How's it going, folks? Jack here. So after watching the latest animations from the Alan Becker channel on animations versus geometry, I've gotten quite the recommendations to watch some more science-based content, and coincidentally enough there are some that also popped on my feed, namely one here by the YouTuber called Joseph Newton. Quite a nice name to have with regards to what we're about to talk about today, which is cursed units. Let me tell you something. As a European, I am damn happy to always talk about how great the metric system is. It's just wonderful, things just flow quite clearly. However, as a physics graduate, another thing that I appreciate way more is the SI units, which stands for Système International, which is just over-encompassing all of the units that we use in just very much science-related stuff that also encompass stuff that are in the empirical system. And in it, for the most part, the units just tend to work pretty well. However, not every units are made equal. There are some that are pretty nice, that are even named after some good inventors, mathematicians to physicists, the likes of Tesla or Newton, simple ones, Euler or Boltzmann, you name them. But once you start deconstructing what those units truly encompasses, it starts getting pretty weird. To explain that before we jump into the video, let me show you something.
Few moments later.
I still have my 3 books that I got for my introduction to university physics. It's like, well, an introductory thing that you will get at most university, I will presume. You get like these 3 books, one for praxis, one for the elementary stuff, and this massive one here. Now, you may notice that this very book is still in its cover, and that's not because I did not need the book. I was smart enough to understand. No, I wish that I could flex with something like that, but absolutely not. It's because there was an ebook variant of this, which was way easier to search into through the computer and of course to take notes. But those 3 books will last you like 2 semesters, wherein there is an introductory exam that has to deal with one thing called dimensional analysis. And that encompasses you understanding how to deconstruct and, well, construct some of the units that you are going to face. As an example, if we're looking at the thumbnail here, we're faced with 4 different units, right? Kilowatt hours is the first one here. Could be anything from just the amount of energy that you use in the house or the consumption of like some machine, whatever. Here we have what looks, I think, the gravitational constant. It could be confused a little bit with if we had a 2 here instead of a 3, we will have the reduced Planck, the Planck constant, because the reduced one is divided by 2 pi. God damn it. Do you see what happens? It's as easy as that to fail a course like that. And over here, if I zoom out a little bit, we have Hubble's constant, which is, well, that one's a slight bit hard to explain, but like the distance that we have from the ever-expanding universe at the rate at which things keep moving apart from each other. I won't get into details. I suppose that the content creator here, Joseph, is going to go through that. And this last one here, I'm not too sure. We are dealing with picoseconds over square kilometers. That must have something to do with something optical. Yeah, so something within optical mediums. But anyways, without further ado, let us jump into the video proper.
There's a website called What If, where cartoonist and engineer Randall Munroe answers ridiculous hypothetical questions with precise scientific detail.
There's a book.
If you're like me,
I've
the
seen
family's
this.
resident science kid who gets all the science-based Christmas gifts, then you've probably already seen this in book form. There's one particular article I want to draw your attention to. Droppings. If you went outside and lay down on your back with your mouth open, how long would you have to wait until a bird pooped in it?
Yep.
Munroe answers this question with a single equation containing a lot of funny units, like poops per bird per hour, in which everything cancels out to give a single figure of 195 years. On the topic of weird unit cancellation, Randall then goes on a tangent into a very commonly used unit which has a similar sort of strange cancellation: gas mileage, or fuel efficiency. I recommend just reading the article since it's very short, but let me give a quick rundown. In the US, fuel efficiency is measured in miles per gallon. How many miles can you drive on a gallon of fuel? But in Europe and also here in Australia,
Liters
it's
per
measured
100
in the
kilometers.
reciprocal form, liters per 100 kilometers. That is, how many liters do you need to drive 100 kilometers?
Yeah.
But a litre is a unit of volume equal to 1,000 cubic centimeters, and a kilometer is a unit of length
All you're
equal to
left
1,000
with
meters. So cancelling things out,
squared.
we find that 1 litre per 100 kilometers is actually equal to 0.01 square millimeters. You can do the same thing with gallons per mile, the reciprocal of miles per gallon, and a typical gas mileage of, say, 20 miles per gallon corresponds to about 0.1 square millimeters.
That's a conclusion to hydraulics. I had the course in hydraulics too. I failed that one twice before finally getting it right. But yeah, to maintain the right levels, I know this kind of example. I suppose that's where he's heading to.
There's a nice physical interpretation of this unit. Imagine driving alongside a thin tube of fuel that feeds into your fuel tank. Your gas mileage is the precise cross-sectional area of the tube, chosen so that the fuel in your tank always stays at the same level as you keep driving.
Yeah.
Units are weird, and in my undergraduate studies I encountered a lot of particularly cursed units. This video looks at 4 of them, which gradually build in cursedness. Let's start with another unit in common usage, kilowatt hours. When we say something like miles per gallon or meters per second, we have a simple intuition for that. How many miles can you drive on 1 gallon of fuel? How many meters is something moving each second?
Pardon? Not this, but that's beautiful. I just noticed that every the note, the composition in the background follows everything that he's saying. I don't know if he does this himself, but wow, that's beautiful. It kind of reminds me of the Bill Wurtz video, right? The history of the world, and that's just very nice. I wish I could do something like that. That's beautiful.
But just as you can divide units, you can also multiply, and this has a different sort of intuition.
Oh yeah.
If your washing machine is running at a power consumption of 2 kilowatts, and it runs for 5 hours over the course of a week, the total amount of energy it uses in that week is the product of the two, 10 kilowatt hours. Like miles per gallon though, we can do some unit cancellation. A watt is actually a joule per second. How many joules of energy is something using every second? So we've got energy divided by time multiplied by time. And since there's 1,000 watts in a kilowatt and 3,600 seconds in an hour, 1 kilowatt hour is actually equal to 3.6 megajoules.
A beautiful thing that we also have here in the EU is the energy rating that we give things. I like that he used the washing machine example because that too tends to vary depending on the appliances, because we tend to indicate hours with like kilowatt hours per annum. So generally speaking, it's often written per 1,000 hours, which is just at the end of the day watts. But again, there's like 8,700 hours in a year. Seconds, Jesus. 8,700 circa hours in a year. So all depending on how long your appliance is running, you get the amount of watts it generates, right? But with regard to the washing machine, we actually have a ratio to the load to energy consumption, because we then have kilowatt hours per grams or per kilograms. So yeah, it gets even more cursed.
You can maybe see now why I think kilowatt hours are cursed. Let's say you wanted to estimate the distance from your house to the beach, and let's say it takes you 20 minutes to drive there, and accounting for traffic, your average speed is about 60 kilometers per hour. Since distance is speed times time, you convert the 20 minutes into a third of an hour and multiply by 60 kilometers per hour to get 20 kilometers. That's what a normal person would do. Writing kilowatt hours is like multiplying the 60 kilometers per hour by 20 minutes and then writing your answer as 1,200 kilometer per hour minutes.
Yeah.
We'll see more of this cancellation later in the video, but first I want to say something about this general process of multiplying and dividing units.
Gravitational constant.
Most physical constants have units. For example, the gravitational constant, which relates mass to gravitational force, has units of cubic meters per kilogram per second squared. Let's see where this unit comes from. The gravitational force between two objects is proportional to their masses and inversely proportional to the square of the distance between them.
Yes.
That means that the gravitational force between two objects is equal to the product of their masses divided by the distance between them squared, and then multiplied by some conversion constant, g, which we don't know yet but is the same for every pair of objects. To verify this, you can either do an extremely precise measurement with extremely precise equipment, or you can do a bunch of maths to this model to derive the orbits of the planets and then do some astronomy to see if it lines up with the actual orbits of the planets. If you do this, and you're working entirely in SI units, you'll get that g is about 6.67 times 10 to the minus 11.
Yeah.
But there's a problem. The units in this equation don't match up. We've got force on the left and mass squared over length squared on the right. So let's rearrange things to get this constant g by itself. Now we can see that g is actually in units of force times length squared divided by mass squared. If we then use the fact that force is mass times acceleration, and acceleration is velocity divided by time, and velocity is length divided by time, we get units of length cubed divided by mass divided by time squared.
And then...
And this isn't just a technicality. If we're working with different units, the gravitational constant will need to be converted into those units. For example, if we were measuring mass in pounds and length in feet, we wouldn't get 6.67 times 10 to the minus 11. Instead, we would get 1.07 times 10 to the minus 9.
Yes, these were the very first things that really started to annoy me when they had to do that through dimensional as... Wow, that became a tongue twister suddenly. Through dimensional analysis, because you become way too familiar with this here on top, and you go like, yeah, obviously I remember that. Or I just need to remember what factorial we are dealing with here, right? It's to the minus 11th. Fine, that's always the constant. We don't need to remember whether it needs to end on the 7, 4, 6.7. We tend to keep it at that. But then on the exam sheets, they hit you with feet, pounds, and seconds. You go like, what happened?
This process of only looking at the units in an equation is called dimensional analysis. And amazingly, it can actually be used to figure out what equation you should be using in the first place. There's a good number file video on this that I've linked in the description.
Bomb blast radius.
Okay, those examples were both pretty quick. The next one is going to take a bit longer to explain. It's called the Hubble Constant, and it's measured in kilometers per second per megaparsec.
Parsecs, yes.
Oh boy.
The parsec is beautiful.
With some history. During the 1920s, physicist Alexander Friedmann derived a model for the shape of the universe based on Einstein's field equations, suggesting that the universe could be expanding, a result supported by the fact that distant galaxies always seem to be moving away from us. Several years later, multiple researchers, including Georges Lemaitre and Edwin Hubble, independently found estimates for the rate of expansion. The idea is as follows. Take a sample of a whole bunch of distant galaxies, and for each galaxy measure two things: how far away it is, and how fast it is moving away. If the universe is expanding, then we would expect galaxies further away to be moving away faster. So take all the galaxies and plot them on a graph, with velocity on the y-axis and distance on the x-axis. The galaxies tend to fall along a straight line, and the slope of this line, now called the Hubble Constant, describes the rate of expansion of the universe. If you do all the measurements, you get a slope of approximately 70. 70 what? 70 kilometers per second per megaparsec.
Yes, this has often been depicted with like the risen bread model, where like you take a bunch of raisins and you make it, or you put it on the dough and then you bake it, right? If you imagine yourself standing on one of the raisins, as the bread expands, you will see the raisins that are closest to you moving slower, where those that are further away from you moving way faster. So that's sometimes how it is depicted, the constant rate at which the universe is expanding. Some have pushed this all the way up to 74 kilometers, and some have found it to be slower because, as explained before and as shown in the figure here, some areas move faster and some slower. It's not actually constant. But yeah, it's generally just this approximation. Also, I want to say that the English version of it, at least the one that uses miles, so empirical, I guess would be the right word to use here. It's a lot more beautiful because it takes into account the number 42, because it's 42 miles. And then it is per light years, I think per 30 light years that it is expressed per second. And what's even more beautiful about it is that the Hitchhiker's Guide to the Galaxy, which of course has popularized the answer 42 being the answer to everything, takes inspirations from that as a solution. So it's pretty nice. Oh, message. Sorry, let me turn off my phone here.
That means if a galaxy is 1 megaparsec away, it's moving at roughly 70 kilometers per second away from us. If a galaxy is 10 megaparsecs away, it's moving at roughly 700 kilometers per second away from us, etc.
Yeah.
Okay, but why megaparsecs? What is a
far.
parsec? It's about 3 times 10 to the 16 meters, and to explain why we're using parsecs, I need to explain how you actually measure the distance to a faraway galaxy. If you look at something in the sky and it looks small, it's hard to tell if it looks small because it's actually just small, or if it looks small because it's far away. The way you get around this is by pointing 2 different telescopes in 2 different locations at the same object and measuring the difference in the angle between them. You can then do some trigonometry to figure out the distance. The way we define a parsec is as follows. The distant object is 1 parsec away if the angle between the 2 telescopes is 1 arc second away, and the distance between the telescopes is 1 astronomical unit.
Ooh.
What is an arc second?
Yeah,
it's a 60th of a 60th of a degree. And what's an astronomical unit? It's the distance between the Earth and the Sun.
That's nice.
How did we get 2 telescopes that far apart? Well...
Yeah, we don't have to. We just take one here and then 6 months later as the sun has gone...
I beg your pardon?
The sun. Well, great, Jack. You just perpetuated people's geocentric model. No, after the Earth has done half a lap around the sun.
Easy. You actually only need 1 telescope. Just take 1 observation in January and a 2nd observation in July. So you have 2 observations with a distance between them of 2 astronomical units.
Yeah.
I don't know where the 2 factors in. Obviously, I'm brushing over a lot of details here. So if you're an astronomer and you're doing lots of measurements on a daily basis, it makes sense to record distances using parsecs, because it follows directly from how you measure things in practice. The speed of galaxies, on the other hand, is calculated using redshift, the Doppler effect for light. And for this, there's not really any reason to use anything other than SI units. So when we're comparing velocity and distance, we get a figure in kilometers per second per megaparsec.
And remember that the Doppler shifting is just with regards to like the perception of the change in frequency with respect to the observer. You've seen and heard this many times before. The siren from a police car, an ambulance, when it gets closer to you, the pitch is way higher. The further it is, the pitch is lower. And so goes with the frequency. In the same way does the frequency come in light form, because we can just measure that to radio signals or to the 1 millimeter hydrogen? No, 21 centimeter absorption lines. It's a medium within which we can observe the light, wherein things that are moving closer to us, right, lower pitch and lower frequency are depicted as being blue, whereas things that are moving further away from us with a higher frequency or longer are depicted as being red, as they are being red shifted and blue shifted. So that's kind of how you observe that. The tricky part then can be when we take into account the different type of stars that we're dealing with. Younger stars are bluer because of the higher hydrogen content, so they are more explosive, they're bursting with energy, whereas older stars have a higher metallicity, which makes them red. So it's like, fuck. So you need to know to factor a bunch of things when you have to determine which is which.
But once again, we can do the gallons per mile trick. We're dividing velocity by length, and velocity is length divided by time, so if we convert the 2 lengths into the same unit, we get that the Hubble constant is about 2.3 times 10 to the minus 18 inverse seconds. You can check this by yourself. Type into Google 70 kilometers per second per megaparsec in this format, and it will convert it for you into 2.3 times 10 to the minus 18 hertz.
Yep.
Okay, I have something else to explain.
Frequency.
Hertz is a measure of frequency, and it's equal to inverse seconds. Why? Well, let me give an example. Let's say a sound wave has a frequency of 100 Hz. That means 100 waves are entering your ear every second. A different way to measure this would be to measure the time interval between two consecutive waves, which in this example would be 100th of a second. So you can see that the period of a periodic process, measured in seconds, is the reciprocal of the frequency, measured in Hertz. So to make sense of the Hubble constant, let's flip it upside down to get a number in seconds. Converting gives about 14 billion years, which is a very rough approximation
The age of the universe.
for the age of the universe. Now, the intuition behind this is as follows. Suppose a galaxy is moving away from us. If we assume it's always been moving at the same speed, then at some point in the past, it must have been right next to us. How long ago was this? Well, time is distance divided by speed, so it will be the distance to the galaxy divided by its velocity. But this is just the reciprocal of the Hubble constant, so the galaxy began its journey away from us 14 billion years ago.
Yep.
But this is true for every galaxy. That means 14 billion years ago, all the galaxies in the universe were on top of each other, and that sounds an awful lot like the Big Bang. Now, as it turns out, this explanation is actually completely wrong. The rate of expansion of the universe has changed dramatically over time, so there's no reason to expect galaxies have always been moving at the same
rate,
speed.
exactly.
The Hubble constant is not actually constant in time, but rather constant across all galaxies at each fixed point in time. This is why it's sometimes called the Hubble parameter instead. What makes this so particularly cursed, though, is that the actual age of the universe is about 13.7 billion years, which in an absurd coincidence is extremely close to the 14 billion figure provided by the Hubble constant. Why are these two numbers similar? There is no reason for these two numbers to be similar. Is there an intuition for the Hubble constant measured in Hertz? Sure, it's how many times the universe can expand from the Big Bang up to the size it is today in the span of a second.
Yeah.
Right. I guess some ways of writing units just don't have a nice interpretation.
And that's the thing, that's the beautiful and also scary thing sometimes. Like, how do these things fit together? Well, they just do. There is a notion behind it that just makes sense. Have we proven anything otherwise yet? Not really, we keep looking, but the math is sound. But still fucking cursed. And
now, as we saw
this
in
one
the
is
gravity
interesting.
example, units sometimes just pop out of equations without any explanation. In this context, it's often more natural to write negative exponents for division, so instead of writing cubic meters per kilogram per second squared, we write meters cubed times kilograms to the -1 times seconds to the -2. But this raises a question. If we can get negative powers, then can we get fractional powers? Can we get irrational powers?
Oh god.
As it turns out, yes.
Yeah.
Occasionally you need to describe a relationship which follows a complicated power law, and that power carries over to the exponent on the units. There's one particular example that I want to go through, one which I encountered while writing an assignment for an optics course.
Yep.
It's called...
I was right, it was optics. I didn't quite realize it was polarization. And dispersion are the same. Okay, yeah, okay. That... Dummy.
Polarization mode dispersion, and it has units of picoseconds per square root kilometer.
Oof.
The speed of light in a vacuum is constant, but inside a substance like glass, light slows down, and the amount by which it slows down depends on properties of the light like frequency and polarization. This is why a prism can be used to split light into its component colors. Each color is a different frequency and moves at a different speed through the prism, resulting in it bending in a different direction. This is a big problem for optical fibers, which use light to carry information. A single pulse of light can be split up into component frequencies which all move at different speeds through the fiber. The overall effect of this is that the pulse gradually changes shape and spreads out as it travels, an effect called dispersion. Dispersion limits the rate of information transfer because you need to send pulses far enough apart that they don't blur together. Dispersion is measured in units of time, typically picoseconds. If you send a perfectly narrow pulse through the fiber, the dispersion is essentially the delay between the front of the pulse and the back of the pulse reaching the end of the fiber.
Yeah.
There are a couple of different kinds of dispersion. The one I've just described is chromatic dispersion, where the different
colours,
frequencies
yeah.
move at different speeds. This builds up linearly over the length of a fiber, so it's measured in picoseconds per kilometer. How much does the pulse broaden in picoseconds for every kilometer traveled? Depending on the fiber, there are ways to counteract this, but once you've accounted for it, you run into a different kind of dispersion called polarization mode dispersion, or PMD. Light is made up of oscillating electric and magnetic fields, and the angle of these oscillations is called the polarization. PMD occurs when different polarizations move at different speeds through the fiber. This seems strange. If the fiber is perfectly cylindrical, then surely it doesn't matter whether the light is oscillating vertically or horizontally. But that's the point. It's hard to make something perfectly cylindrical. Remember that optical fibers need to stretch over many kilometers, so over that vast length, there's probably going to be some small impurities which make one polarization slightly slower than another. But unlike chromatic dispersion, which is measured in picoseconds per kilometer, PMD is measured in picoseconds per square root kilometer. Why is this? Let's construct a simple model and try and understand it. Let's send a pulse of light down the fiber made of only two polarizations, one vertical and one horizontal. Let's define the dispersion as the time taken for the vertical one to reach the end minus the time taken for the horizontal one to reach the end. So if the vertical one moves faster, then the delay between them is positive, and if the horizontal one moves faster, then the delay between them is negative. We're interested in the absolute value of the dispersion,
so
but keeping track of the sign is also going to be important. Now, there's going to be random impurities in the fiber, tiny defects from the manufacturing process. Each impurity will randomly cause the vertical and horizontal polarizations to move either faster or slower, making the dispersion either increase or decrease. Let's be super rough and assume that the dispersion has a 50% chance of increasing by some fixed amount every meter, and a 50% chance of decreasing by the same fixed amount every meter. What we now have is something called a random walk. What we're interested in is how far this random walk moves away from zero, and the
oh no, this reminds me of our introduction to Python, how we were tasked to, well, produce random walks for, I think it was stellar dispersions, and then you have the random forest afterwards that, oh, no, I don't even... Bad memories when we used to struggle before everything became more or less like, formulaic.
Expected value of this quantity turns out to be proportional to the square root of the length of the random walk. I'm not going to delve into the details of why this is, because this video is already long enough as it is, but it's not too hard to prove. So what this means is that the total absolute dispersion, measured in units of time, is, on average, equal to some constant times the square root of the length of the fiber. In order for the units to cancel out, this constant, which is the PMD of the fiber, has to be in units of time divided by square root length. Which is why, if you look up a specification for an optical fiber online, under polarization mode dispersion, you will find a quantity measured in picoseconds per square root kilometer. I have seen other strange exponents on units. While doing research for this video, I found a paper on pulsar scintillation, whatever that is, which involves something called a scattering measure, measured in units of parsecs times meters to the minus 20 on 3.
Yeah, I was about to say, pulsars are essentially just the electromagnetic pulses that we're receiving from neutron stars, which in turn are just giant galactic nuclei, because they are so bloody dense that both the proton and neutron just almost start fusing together. But when we are observing them, we take into account the refraction from like the electrons that are sent from them. And that's like something, I want to say, to the minus 13th power in centimeters. So I get the, yeah, the scale here, but where with parsecs involved, I don't know exactly why it's minus 20, but with parsecs involved, I don't know exactly why it's to minus 23rd. It's interesting.
I personally find picoseconds per square root kilometers more cursed though, just because square roots themselves are also kind of janky. Funnily enough, the optics assignment wasn't the only encounter I had with random walks in 2021. I was also doing a research task involving stretching polymers, specifically DNA, and from Monte Carlo simulations, I found that the sidewards deviation of a DNA molecule also followed a random walk depending on the length of the DNA. Which makes sense, because a polymer has the literal shape of a random walk.
Yeah.
But what's weird about this random walk is that the length is measured in nanometers, while the sidewards deviation is also measured in nanometers. And so with a bit of hand-waving, I was able to include in my research paper the most cursed unit I have ever written, nanometers per square root nanometer. Have you encountered any other cursed units? Put them in the comments. I want to see the most ridiculous units known to science.
Oh.
I think all the places where science is mathematically beautiful are massively overrepresented, and sometimes it's just fun to see all of the places where the universe is completely gross and inexplicably awkward.
Absolutely.
If you share the same sentiment, then subscribe, because you can expect more cursed mathematics from this channel in the future.
There's a part 2! There's an absolute... Oh, okay. We're watching this one next. Well, in terms of things that are cursed, I would say that immediately... Well, in terms of things that are cursed, I want to say that the one that springs to mind immediately is anything that has to do with radii, or radiance, because we spoke about the hertz before, right? That's a perfect example, actually. Hertz, second to the minus first power. Then we have angular frequency.
Bruh.
It's the same thing. What the hell? Also, if I pull my astrophysics books here for a little bit, I could show you the appendix of some of the unit conversions. Those are likely to freak you the hell out, because they are mad. Where is it? Here we are. Units and conversion. Let's move a bit closer. We have our units, doesn't matter really much. Some conversion factors, and here we go, the physical constants. Oh god. Like, for example, the Boltzmann's ones and the black-body constant, right? You have joule and per cubic meter squared or cubed, and who thought that Kelvin to the minus 4 power was a no. Units as cursed. That's the conclusion of the video. Guys, thank you so much for watching this video. I'm looking very much forward to part 2. This was hilarious. Anyways, wish you all to have a wonderful day. If you liked the video, of course, please subscribe. Please do make sure at least to go and subscribe to Joseph Newton there. I like the explanation. Very well done video. And look forward to part 2. That being said, see you guys in the next one. Bye.